Okay, let's do this. So you guys can see my screen now.
Yes.
Okay, great. Okay, hi. So let's just go straight into the matter. What is computation? What do you guys think it is roughly? Anyone wanna try? Give it a shot. There's no right or wrong answers here. I should look at the chat while we're at it. Let's see. Chat. Making computer go burr. Okay. The act of computing, math. Okay, some very interesting answers there. Grinding numbers. Okay. All of these are true to varying degrees. So let's see what it means. I mean, so our compute is new. First of all, I claim it isn't. There is, for example, this. I still can't say it properly. There we go. It's an ancient Greek astronomical computer, actually. Kind of looks like this. Yeah. Mechanism, not the place. So I forget how old it is, but it might be a few hundred, if not a few thousand. It's got to be a few thousand years old. So this thing was an ancient little computer. It wasn't universal. I'll talk about it. It doesn't do all possible computer programs you can think of, but it can predict some things in the sky, which is very impressive, especially for that time. Or it could have been aliens who built it. Who the hell knows? I'm joking. Don't quote me on that. Okay, but anyway, there's also ancient Indian algorithms. If you read the ancient Hindu texts, there's some examples of people coming up with interesting procedures for calculating things. The Greeks also had them. Euclid had his famous greatest common divisor method. I encourage you to look it up. It's extremely simple. But it's an example of what today we would call a computer program. An algorithm is just a computer program. Some might say it's kind of like a recipe. For cooking food, same thing. It's kind of like a very detailed series of instructions telling a computer exactly what to do when this and that happens and given this input, right? You produce that output. That's basically what computation is. We'll talk about why we got there. Why did we even bother coming out with computers? Leibniz, who was, among other things, a mathematician, co-discovered calculus along with Isaac Newton, and they both fought over who came up with it first. And apparently, Newton was much better at controlling the media back then, the scientific media at least, and so he got most of the credit for it. But Leibniz also probably very likely came up with it independently, but he's not famous for it. But anyway, he said, look, we don't just need a calculus for calculating infinitesimals. We can also probably even have a calculus for morality. Whoa, where the hell did that come from? What does he mean? He's saying, look, the same way we can resolve disputes in mathematics objectively by calculating things, why not solve problems in morality that way? So we'll come up with this formal system that will tell you whether or not something is ethical, for example. Sounds like a crazy idea. We'll talk about why this is important later. All of this is covered very nicely in George Dyson's book, Darwin Among the Machines, by the way, which I highly recommend. It's a nice history of computation. Leibniz also, I just found out this myself recently, he came up with the idea of bits. What are bits? Binary digits, just 0 and 1. Uh, you can talk about, you can think of it as like the base language for a digital computer. Now, after that, in the late 1800s, Charles Babbage um, and Lady Ada Lovelace, who is said to be the world's first programmer, they came up with the idea of something called the difference in analytical engine. See, back then, before these guys came up with the idea of using a machine to calculate things, human beings would go through this very laborious procedures to come up with things like logarithm tables, for example. You would basically look up very thick books and go to this row and that column to find the answer that you're looking for. Imagine calculating things this way. It's very not only error prone, but also very tedious. So this guy said, why not just make machines to do all this, take out all this tedium for you? So that's arguably a precursor to computation. As someone said here, you can think of computation back then as just a number crunching machine. And that's called arithmetic universality. That is a machine that can do all the arithmetic that can think of: addition, multiplication, division, you name it. But this is a rather boring way of looking at computers. And I would say, and I'm going to argue here, it's not my original idea, but I'm going to try to present other people's ideas and argue for it here, is that this is a rather incomplete view of looking at numbers, rather boring way to look at it too. Okay, anyway. Now, in the history of computation, we come to this very curious fellow called Georg Cantor. Pretty sure I'm butchering his name, but um, he was a mathematician, but also very deeply, very religious. And he wanted to understand God. And he said, what better way to understand God than to understand infinity a lot better? And he wanted to be very, very precise about infinity mathematically. So the first question he came up with is, how many kinds of infinities are there? Sorry, go ahead. Did someone ask a question? No? Okay. So he said, how many kinds of infinities are there? What do you guys think? Take some guesses. One, two, infinity? Okay, that's a good answer. And it's not precise, but it turns out there's something called the transfinite arithmetic. Look it up. It's crazy. It's one of the most mind-bending things you'll ever see in your life. And it's mathematically precise. There's nothing unrigorous about it. But basically, Cantor found out there's something that we call the set of natural numbers. It's just the counting numbers. We all learned this in kindergarten, right? 1, 2, 3, 4, blah, 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 blah. That's the smallest set. And the size of this set is the smallest infinity. And then he showed that the set of real numbers, and I'm not going to get into details why, but real numbers are, you've seen them. They've got decimal digits, expansions. You can see intuitively why they are larger than the set of natural numbers. But to be precise, the size of the set of real numbers is much larger. That is a different kind of infinity. That's the next level of infinity. So already we have two classes of infinity here. We've got infinity 0, and then there's infinity 1, and then there's infinity 2, and it goes on and on and on and on. It doesn't end. And God, as you can imagine, is the absolute infinity, unreachable. So a lot of mathematicians were disturbed by this. They were like, this is religion. This is not mathematics. But other mathematicians like David Hilbert said, no one shall dispel us from this paradise that Georg Cantor created for us. So he's saying, look, let's not argue about this. Let's pull a Leibniz. And remember what Leibniz said earlier. If there's a dispute about whether something is mathematics or not, think about it. What does mathematics mean? So he's saying, if someone gives me a proof, someone like Cantor walks up to me and says, I claim that this proof is true. And you dispute whether it is true or false. That's basically what mathematics is. We're interested in all possible true statements, correct? About, say, the integers. So we feed this thing to a machine, let's say, think of it. He didn't quite use these words, but it was the idea. Can we have a procedure that tells you whether or not, if someone gives you a mathematical proof, whether it is true or false? Basically, you want a procedure that can answer all true or false questions. Think about how powerful that would be. So indirectly, he was specifying a computer, although he didn't quite. Turing came out with it later about. So that's the infamous 1900 lecture in Paris. That was one of the 26 problems, I think, that Hilbert posed back then. Some have been solved. I think some might still be open to this day, but computation is one of them. The so-called decision problem has been solved definitively by Alan Turing and friends, which I'll explain soon. By the way, Gene, I have no idea what the sense of time is. So please stop me if I'm going too long or too fast. So a fellow called... Sorry, go ahead.
The class actually technically runs till 10:50. We certainly I don't think we'll intend on running that long. Generally, that's a very long lecture, but so you have plenty of time.
Okay.
So I wouldn't worry about it. If it does get to 10:50 and you're still talking, we'll just quietly slip away and you can keep going.
Yeah, exactly. So I see some students have already said countable and uncountable infinities. Good. Okay. So if you guys are not familiar with this, you should look it up. It is mind-bending stuff. It is really beautiful stuff too. Anyway, some of you might have heard about Kurt Gödel and his famous incompleteness theorems. He came up with it in the 1930s to try to answer. Actually, he was trying to bust another system. So basically, damn, I forgot to mention this gentleman. How could it slip my mind? But there's two gentlemen, a student and his teacher, actually. Bertrand Russell and Alfred Nord Whitehead. They came up together and said, let's create a system called Principia Mathematica, which is, sort of a name after Newton's own work. and said, let's create a formal system that you can think of it as a system that will produce all true mathematical statements. And they're saying, let's get rid of all this contradiction stuff. Let's create this clean, you can think of it as a programming language, actually. There are many ideas that we borrow from it, such as types. And they're saying, this Principia Mathematica will produce all true mathematical statements, okay? Such as 2 plus 2 equals 4. And they came out with a proof for it, but it took hundreds of pages. And the joke apparently is that Russell apparently put a £5 note. They didn't have Bitcoin back then. But he put a £5 note into the middle of the book to see whether anyone's actually read it. And apparently when he checked back into the library years later, no one had still claimed that note, proving that nobody read this very, very extremely tedious work. But anyway, the point is that they were trying to mathematicize mathematics. Imagine that. You want to formalize what mathematics means, make it so objective that there's no argument about whether something is correct or not. And I don't want to talk about how Gödel busted their idea because it's complicated. It's not too easy to explain. And I claim, actually, I'm stealing from Scott Aronson here. It's much easier to understand what Gödel did using computers. Gödel's work wasn't actually wasn't constructive in that sense. It's very strong negative results, which is good. It talks about the limitations of what machines can do, basically, but it doesn't tell you how to build these machines. Alan Turing had a completely independent, very refreshing. I think he was aware of Gödel's work, but this guy came up with a completely new approach altogether. It's so refreshing and so actually arguably very simple to understand, and you can explain it very easily to high school students. What Turing basically came up with, he said, look, forget everything you thought you knew about mathematics. And they didn't have computation back then. This guy basically discovered computers. So how do you describe computers without having run into computers? He said, what if I had to explain to another human being what to do to be said to compute something? Let's say a real number. I need to tell this person every single little step to do, right? Now, basically, that's what I'm going to make this machine. This machine is a very, very dumb thing that knows how to do a very few simple things. I have to tell it exactly everything. But once I break it down, it knows how to compute that real number too, right? So actually, before computers actually referred to human beings, ladies typically, who performed all these tedious calculations themselves on pen and paper. People were more sexist back then. So Turing came out with this machine and said, what do I need to do? What does this machine need to look like for it to be, it has to be very simple. So actually a Turing machine is very, very simple. You can think of it as like a typewriter, because that's what they had back then. They didn't have computers, but they had typewriters. So he said, imagine a typewriter, it's got a head that can read and write. And you've got this infinitely long tape. It doesn't have to be actually infinite. It's just that's memory. As it needs memory, you give it more paper, for example. And on this paper are ones and zeros. Actually, could be any alphabet of finite size. But let's just simplify things and say zeros and ones, because you can reduce everything to zeros and ones. So in this input, right, you give it enough working paper to give it your problem, zeros and ones. It also contains the program. So not only do you specify the program on this piece of paper, you also specify the input for it to work on. And then it would go about, it has something called state, right? So it kind of remembers, oh, I was doing this. So if I am in this state and I see a 1, then I'm going to move left, or I'm going to move right, or even stay in the same place and overwrite that input if I wanted to, or I just keep it, or I can delete it. It's a very simple machine, right? There's nothing very complicated about this. But this machine turns out to be equivalent to the most sophisticated computers that we have today, and even arguably quantum computers. The only difference is in speed, not in the power of their computation or what it is that they can and cannot do. Fundamentally, they're the same. But as far as we can tell, practically speaking, quantum computers are faster, but they're not able to solve uncomputable problems that Turing machines cannot do. So like Feynman said, so I don't know whether you guys, I forget what the game is called, but there's a game, a board game that you can play with your friends. And the objective is that one of you is the bomb diffuser. and you have no idea how to defuse the bomb. And your friends have to tell you every single little thing to do, like what color and everything. So a computer is like that. You're telling a very, very, like Feynman said, a very dumb clerk, no offense, who knows how to do only a few very simple things, exactly how to defuse the bomb or how to multiply in terms of addition. Imagine you only knew how to add numbers. How do you then implement multiplication? Right? You see? So anyway, what the hell is the point of all this? Why did Turing come up with this damn machine in the first place? What is it useful for? Well, he said we can try to solve Hilbert's decision problem. He claimed, I can actually answer it once and for all. And he says it is impossible. It is impossible to build a machine or procedure that can answer all true or false questions. And the proof is remarkable. Keep talking and nobody explodes. Exactly, that's the game. I should play it one day myself. But that's the story of every programmer's lives. Keep talking to the computer and nobody dies. You need to tell the computer what to do. Okay, so Turing found that he has what he calls the set of Turing machines, right? And there's a countably infinite number of Turing machines, and they can compute an countably infinite number of real numbers. So is there anything this Turing machine cannot do, these Turing machines cannot do? And the answer turns out to be yes. And he gave it's called the halting problem. It's very, very simple. I don't know whether you've used a Mac or any other computer, maybe even Windows. If you're loading a program sometimes and busy doing something, you might see the beach ball of death. It's just spinning forever and you're never sure whether it's ever going to stop computing. That's basically the halting problem. If I have a program and an input, can you just tell me, given any program, whether it will eventually stop computing or not? Because you can imagine that there are programs that never stop. There's infinite loops, for example. While true, do this thing forever. So for very simple programs, you might be able to eyeball it and say yes or no. But for complicated programs, let's say 10,000 pages, how do you decide? So can we build a computer program for it? And the answer turns out to be no. And we don't have the time, but it's a beautiful proof by contradiction, and I highly recommend that you take a look at it. So here's Quantum Computing Since Democritus. That's by Scott Aronson. I highly recommend it. He has a lecture, good old Turing and Friends, I think. And it's free, You don't even have to pay for it. I forget where it is exactly. There we go. This is blog. You should read this blog also. It's very good. There we go. And he has an explanation here for how to build this contradictory program. So let me give you a rough idea. Think about it. It's really remarkable. Suppose that there is a way to solve the halting problem, right? And let's call it P. And he's saying, let's produce a new program P prime. P prime does a very cute little thing. P prime says, if you give it another program Q, bear with me here, you give P prime another program Q as input. And here the idea that code is data and data is code, it becomes very important. Program is just another bunch of input. In fact, that's what programming is. You're telling the computer, hey, here's a new little program to run. So you give the program on this input, and it does the opposite of what Q does. Q halts if given its own code as input, right? So Q runs on itself. And then if it halts, P prime just does the opposite. It runs forever. But if Q runs forever given its own code as input, then P prime halts. It does the opposite. So now, if you feed P prime to this program, you'll see that we build a contradiction where P prime will run forever if it halts, and if it halts, it halts if it runs forever. It's what's called the liar's paradox. Epimenides, I think, was a Cretan, and he said all Cretans are liars. Well, if that's true, then he's a liar. But that also means what he said is false. So it's a contradiction. You can never decide whether it's true or false. So it's a very cute little thing. Basically, there's an uncountably infinite number of things that computers can never do. It's not a question about space, time, or any such thing. It's just in principle, at least if you don't think contradictions can exist, that Turing machines or even quantum computers can never do, right? There's just no program for it. One example is, think about it. Why is it that we don't have perfect antivirus after decades of work? Is it something empirical or is it something theoretical? It's actually theoretical. It's fundamentally impossible for the same reason. Because for the same reason that you can't solve the halting problem, anything that you can divide two computer programs into. So, for example, whether it's a virus or whether the program is a virus or not a virus, you can't solve. Okay, it doesn't matter how much time you have; it just cannot be done. At least not with digital computers. And now we can understand Gödel through the back. So this was a death blow to Hilbert's program, right? This seems like, oh my God. So Jesus Christ. So it turns out that there's a whole bunch of real numbers that we can never compute. So Chaitin, by the way, uncomputable real numbers. So remember we talked about countable infinity and uncountable infinities. We're going back to Cantor here. It turns out that you can think of computers as being able to reach into like the equivalent of the set of natural numbers. That's all the things it can do in terms of computable real numbers. But it can only get into that thin, infinitesimally small slice of all possible real numbers, which is uncountably infinite. So using measure theory, you can show that it's zero. So practically nothing. So Chaitin, who's another famous computer scientist, says, so then why should I believe if I can't prove what its bits are, if I can't compute it? Why should I believe that these real numbers exist? Maybe only computable real numbers exist. Maybe we're going slightly into metaphysics here, but I thought it was worth talking about. And then now we can go through Gödel through the back door. So the next time you go to a cocktail party after the whole pandemic is over, when someone brings up Gödel, you can tell them exactly what Gödel meant. Gödel said basically two statements about when it comes to computers and mathematics. The first incompleteness theorem basically says that there are true statements about integers that you can never prove. Because partly, I think fundamentally, basically you run into contradiction problems all over again. And the example, he did it by basically, remember the liar's paradox I talked about earlier? All cretins are liars. He basically coded it in Principia Mathematica and showed that, and his in English it basically says this sentence P basically translates to in English, this sentence is unprovable. This statement is unprovable, sorry. So think about it. If Principia Mathematica proves it, it's in trouble. It's inconsistent. So it's true that it is unprovable. But if it proves it, it's in trouble. Then whether we say it's inconsistent, then it's produced a garbage statement that should not have been proved in the first place. So it's true, but the problem is you can't prove it. It's hilarious. So you need to go you need to add it as you need to build different hierarchies of mathematics, basically. There's no such thing, okay, let me put it this way. There's no such thing as a closed, complete formal system of mathematics. Okay, you have to keep adding new axioms and maybe new rules of inference. So mathematics is not a dead process. This is what another mathematician, Emil Post, was saying. Hilbert's mistake was to think that mathematics is a closed process that you can trivially mechanize like this, and it turns out not to be true. The second incompleteness theorem, by the way, it's more subtle. I'm not even going to bother, but you should read Scott Aronson's explanation of it, which is brilliant, approaching it from computation. It basically says that you cannot prove the consistency. You cannot use Principia Mathematica, a system like Principia Mathematica, to prove its own consistency, to prove that it cannot produce contradictory statements and say that something is true and false at the same time. You don't want a system like that. A system like that is useless. But guess what? You can't use Principia Mathematica to prove its own consistency. Then you might need stronger systems that can then talk about the lower system. Sorry, go ahead, Gene. I can't hear you.
Better unmute. Now, I didn't mean to interrupt you mid-sentence. I just wanted to get on the queue for talking. I actually, when I got admitted to my master's program, they sent me, I think it was a little Godel challenge email. I got admitted, and a few days later, I got an email saying, this is from the IT department. It's just a test. Please pay no attention to this email.
That's like
And
a
I
Turing
said,
test.
wait a second. I said, if I don't pay attention to this email, I'm doing what the email said, aren't I? I'm paying attention to it. I was never able to finish the master's program. I just got stuck on that one email, and that was it.
Actually, yeah, that's a great story. There's actually a short story. I need to find the story and send it to Eugene. I think you like it. But it's in the book The Mind's Eye by Hofstadter and Dennett, edited by them. It's an interesting short story where someday someone makes the mistake of finding the equivalent of a Gödelian sentence but for the human brain. And so whenever someone hears this terrible secret, they just get stuck forever. It was rather scary, actually, to think that it might be possible. But actually, think about it. Human beings are, even if, yeah, sorry, go ahead.
Monty Python has a skit similar where in World War II, the Germans invent a joke so funny that anyone who hears it dies laughing, and they have to code it up in tiny words, and they can only teach each soldier one word of it at a time, because if anyone knows more, they wind up hospitalized.
Exactly. You see, maybe that's why they lost the war. It's a little known secret. Sounds like my type of jokes. Yeah, so be very careful going into computer science, by the way, and mathematics and all this logic stuff, because a lot of people who unfortunately studied this thing somehow went mad. Unfortunately, like Emil Post, for example, was admitted to an asylum. Gödel starved himself to death. It's a very sad story. His wife died, and it's a very paranoid fellow. In some sense, he was right. The doctors are rather dangerous people, iatrogenics and all that stuff. But he didn't trust them, so basically refused to eat anything and just died. It's very sad. Turing committed suicide. Nobody knows exactly why, but the UK government back then found out that he was a homosexual and decided to chemically, punish him. It's not pleasant anyway. Some think it was a chemical experiment gone wrong because he's a rather versatile scientist. He might have accidentally consumed an apple laden with cyanide. Anyway, my point is this can be rather dangerous stuff. So be careful. Anyway, so Turing was also, the genius of Turing is not only did he come up with a very simple way, he came out with a very damn useful machine, even though there's all these limitations to this machine. I mean, here we are talking remotely over a computer today. Imagine if we didn't have it. Imagine going through the pandemic without computers and the internet. Well, it might have been better, actually. Maybe we would have had more Principia mathematics than Newton's, who knows. But the genius of Turing was to say, wait a minute, I have all these countably infinite machines. I don't need a countable infinite number of machines. I just need one. And I call it the universal Turing machine. Well, he didn't name it after himself. Wasn't that egoistic. But it's the universal machine that can simulate all machines, including itself. So you can have a machine instead of a machine instead of a machine, like a recursive, kind of like an Inception kind of thing. And so basically, ever since then, people have been asking the question, well, what if Turing was wrong? Is there something more powerful than the so-called Turing machines? And other people like Alonzo Church came out with lambda calculus, neural networks, you might have heard of them. Big thing in AI now. Neural networks was actually partly invented by a psychologist, Herbert Simon, I think, who teamed up with a mathematician. And both of them said, yeah, we call these things neural networks, and we know they're very pitiful. It's not nowhere near close as rich as the human brain, but it's still universal in that it can do everything that a Turing machine can do. So that's interesting. Cellular automata, x86 chips, ARM chips, Android, iOS, macOS, Windows, doesn't matter. The point is Python, Java, they're all the same. They can all do exactly the same computation. Right? And so there's been several decades of this, nearly a century, and no one's been able to do better. So it's not a proof. It's just a thesis. It's a claim. Nobody knows why we're not able to do better. Is it a fundamental thing about our physics? We have no idea. But and then Turing also, shortly before he died, also wrote a paper called "Can Machines Think?" I highly recommend you go and read it. Whether or not you think it's possible, it's interesting that the man who came out of computers At the end, you might have heard of the famous Turing test. I don't know if any of you saw the movie about him. I haven't. I don't want to, because Hollywood always makes shit up. But oh, sorry, I'm not sure if I'm allowed to swear, but maybe bleep that out. But he basically came up with a test that has its flaws that you can use to determine whether or not something is human or not, or computer. Anyway, so we don't have a lot of time. 4 minutes, 5 minutes. I'm going to try to wrap this up. Look, computers were basically invented, believe it or not for practical results, not as a number crunching machine, but to solve a philosophical problem. That sounds rather obscure in hindsight. Like, who gives a crap about this nonsense? Practically, you don't. But it turns out, so despite such negative results about all the uncountably infinite number of things these machines can never do, they still, nevertheless, turn out to be extremely useful. You can run a spreadsheet on them. You can run, sorry, go ahead, Gene.
Yeah, don't feel pressed for time. As I said, we've got, technically we run until 10:50. So take your time finishing up, okay?
Okay, great. So, oh, 10:50.
Yeah, not 9:50, 10:50. Yeah, I know you're,
Oh.
no, we have lots of time.
No, here's the problem.
Yeah, so no rush.
No, because it's 9:50 for you, but 10:50 p.m. for me. That's why I got confused. That's why I'm rushing. I didn't realize. But better, but yeah, brevity. Anyway, yeah. So the too long didn't read is what is computation, right? Basically, computation was computers are basically a way of mathematicizing mathematics. Is to specify concretely once and for all what we mean by mathematics. And then we can argue about whether this is all. Maybe humans can do more mathematics than computers can, but that's a different argument. But the point is, if you try to make it concrete, this is what we come up with. We come up with something called computers, and they turn out to be useful not just for doing arithmetic. So let's talk about why computers turn out to be so useful. Is it useful just because of arithmetic universality, which, remember, is what Charles Babbage was talking about? He just wanted a machine that would do all the interesting kind of mathematics, regular arithmetic that we talk about. But actually, Lovelace realized, wait a minute, this machine is actually much more powerful than that. It's not just useful for doing the regular kind of mathematics we talk about, solving differential equations and whatnot, computing large factorials. It's useful for doing things that we don't normally think about, like playing chess or playing Go. Right now, we have machines that actually beat human beings at chess. Doesn't mean they're intelligent, generally intelligent, but when it comes to chess, it's hard to beat them. So these machines can do more than just do math as we typically think of it. So what are these machines? So this is where a physicist called Deutsch has proposed what I think is a very useful way to see computers. He says, think of computers as physically universal machines. What does that even mean? So remember, a universal machine is a machine that can simulate all machines, right? Including itself. Which is why you have the Russian doll kind of recursion kind of thing. Deutsch says, think about it. He went back to a guy called Eugene Wigner, great physicist, who gave the first Courant lecture. Courant is a school, does math at NYU also. And his first lecture there was to say, was to ask the question, why is it that mathematics is so unreasonably effective in the natural sciences? Why is this weird, boring bunch of symbols on pen and paper? Why can it even describe nature at all in the first place? Now, whether it can describe all of nature, don't know. But we don't even need to get there. Why is it that we can have equations about how the surface of a star, for example, behaves? Isn't that rather strange? Isn't math supposed to be this very dull, tedious thing about the abstract world that supposedly has nothing to do with reality? So why does it work for reality? And Deutsch says, well, here's what a computer is. A computer is not just a formalization of mathematics. It is a physical system that can copy, that contains all possible motions of all physical systems, of all possible physical systems, including itself. So basically what he's saying is that in nature, there is this thing, this physical systems that we call computers, that can basically, you can think of it as like a universal chameleon or a universal mirror. And a program is just a way of telling this physical system, hey, now copy the behavior of this physical system we call a star. Or now, by giving you this other program, now you copy the behavior of this physical system that we call, climate change. It's not the Earth, it's not complete, but it's a rough model. And we can talk about whether it's accurate or not. But the point is, it can begin to try. So when you think of it that way, suddenly computers and mathematics becomes a lot less abstract. Suddenly it makes more sense. It begins to explain Wigner's question, why is it that mathematics, or equivalently computer programs, why can they begin to copy the behavior of actual physical systems at all? It turns out to be probably not an accident. And Deutsch actually proved this in the 1980s. He said, he basically came up with a universal quantum computer. Richard Feynman tried. Feynman, by the way, made the brilliant observation that nature is not classical, it's quantum, damn it. So our computers had better be quantum, because quantum systems can have an exponential number of states that classical systems can never efficiently simulate. So you need to be able to build quantum computers. But he tried to build universal quantum computers. What's a universal quantum computer? It can simulate all possible quantum computers, including itself, right? Not just specialized quantum computer to do just solve one particular quantum system, for example. It's nice, it's cute, but you can't reprogram it. That's what programming means. You're taking a universal computer and now you're telling it, now run this program, now run that program, and so on. Feynman tried, he failed, but Deutsch did. And Deutsch proved that all finitely realizable physical systems, basically anything around a computer, this universal quantum computer can simulate. So it's very interesting. Some people think, like Wolfram, for example, Stephen Wolfram, think that it's possible to have a computational theory of everything. He's trying. It's called the Wolfram Physics Project. We can talk about whether that's true or not, but assuming it's true, a computational theory of everything is, if it exists, a simple program. Maybe it fits on your t-shirt. Maybe it's a Lisp program, let's say, that when you run it, produces the universe. It's a crazy idea. Nobody knows if it's true, but people are trying. And there's also, and I should mention Chaitan's work here, Gregory Chaitan, who came up with a very interesting way of looking at. So think about it. If you had a program that you could compress, because that's what a theory is. What is a theory? What is a scientific theory? A scientific theory is a computer program. If you take a bunch of facts, observations, and everything, compresses it into a much smaller, it explains how this physical system works. It explains the observations. Think about it. If you can't compress that whole set of facts in the first place, you don't really understand it. It's just randomness. Which actually brings us to Chaitan's algorithmic information theory. He said, what is randomness? Let me define it this way, he said. Randomness, a string, an input, is random if the shortest possible computer program that can reproduce that input is just a print statement that just produces that input. Print that input, that's it. And there's no shorter program for it. That's a rather good description of randomness. So the program is just as big, slightly bigger, constant, than the input. So it's algorithmically incompressible. So it is possible that the universe is actually algorithmically incompressible in that the shortest theory of the universe is the universe itself. So forget about a theory of everything. It's possible. Chaitin was the one who actually told Wolfram about this possibility. Chaitin also came out with a number I call Omega. He's called the Omega Man for this reason. There's a very nice documentary about him on Amazon Prime that I it's called Against Method. And actually, if you look at it, Amazon Chaitin. It's on Amazon Prime. I think it's like $3 or $4. Maybe do it and see if NYU can reimburse you or something. It's fantastic. It's less than an hour. I promise you will have a good time. He's a really super interesting guy. And he kind of looks like Gene. So I suspect they're the same person. Because nobody's ever seen Chaitin since. A bit of a recluse now. So maybe Chaitin and Callahan, they take turns, alter egos. um, yeah, okay. So that's one physical interpretation of computation, which I rather like. That is the least abstract interpretation of computation I've ever seen, which I quite like. It's a physical universal machine, right? A universal chameleon, if you like, to be a little bit poetic about it. We can talk about, since we have a bit of time, does anyone have questions in the meantime? I don't want to make this a boring lecture where I'm blabbing on and I'm ignoring comments. Does anyone have questions? And you don't have to just type it in the chat. In fact, I prefer if you ask, ask our voice. Anyone have questions so far? Yes, Gene, please.
I think I've solved the halting problem.
Go ahead, please.
I just walk around the back computer. I walk around the back and I pull out the plug and the program halts.
Exactly. So the beautiful thing about human beings, right, or life in general, life doesn't waste its time on stupid stuff like this. It's just like, I time out, forget it, I'm done, I move on with life. So living things are very intelligent, unlike computational problems this way. You run to a problem like that, but you say, screw it, I'm done. I move on with life. Go ahead, sorry.
Someone in chat asked, "Wow, is it normal? I don't understand some of the things he's talking about." Yeah, that's no problem, right? So what you're doing is you're hearing about some advanced, interesting stuff. I think that what this should do is whet your appetite to learn more, right? Of course, in a single lecture, this is a field people spend their lifetime studying, right? Someone, like Turing, Alonzo Church, spend years studying this stuff. You're not gonna, in a single lecture, go, oh yes, I now have mastered the theory of computation. No, but hopefully it'll get you interested and you see that there's, wow, even at this fundamental level, there's a lot out there to learn, let alone learning this language or that language or, this machine learning technique. Even at the fundamental level, there's a lot there going on that you could spend your time at working at that level.
Yeah, exactly. Thanks, Gene.
So there's another question.
Yeah.
Yeah. We're not gonna say to you, what year did Alan Turing come up with the halting problem, right? So that's not the level we're going at. I think you should know Gödel, you should know Turing's names, right? Because they're mentioned a lot. So we're not going to try to jam you up on tiny details of the talk. It's the general ideas that we're after, right?
Yeah.
So
exactly.
Just to answer a couple. And when is the first quiz? We will post it soon, and because there are people taking the class asynchronously, there'll be a window. We'll have something like 18 hours in which you may take the quiz, but once you start it, they'll be short. So you'll have like 20 minutes or something to finish the quiz. It's going to be a handful of multiple choice questions. Okay. Yes, and it will be on grade scope. So you'll get it. We'll have an announcement. Okay. Yes, it's timed. So once you start, there'll be a limited time. We want you to watch the lecture and pay attention and then take the quiz. All right, back to you, Trishank.
Thanks. Yeah. Yeah, I'm sorry if I'm giving you it is an unconventional way to present computation. And I think it's a good and a bad thing. It's a bad thing in the sense I might be rambling and giving you, a lot of people might give you, just tell you, give you a dull, dry, technical definition of a Turing machine, and this is what it means to compute, and without going into the history of why people bother to do these things and the philosophical reasons, I think you miss a lot of context, and it kind of sucks away the why I think it's interesting. So there's a computer scientist, Ed Dijkstra, who famously said, computer science is about computers, the machines, as much as astronomy is about studying telescopes, right? It's much bigger than that. It's this whole interesting, interesting array of, thanks, Gene. Yeah, so to answer Kevin's question, since all computers fundamentally have the same simple computations, do brains operate? Nobody knows. This is what Turing thought, but the real answer is nobody knows. It's been unanswered since the 1950s, ever since he posed the question. People are trying. They call it artificial intelligence now. But I think anyone can take a look at these things and say they're still, for things like AlphaZero, remarkably impressive, very impressive. In fact, recently Google managed to apply this to protein folding and come up with apparently much more protein folding. It's a problem of figuring out what 3D structure sequence of, I believe it's RNA now. Yeah, because RNA codes for protein. So you have the sequence for the alphabetical sequence for the protein, and now your job is to figure out the 3D structure of the protein, because that's what actually determines the function. Again, this is my rough understanding as a computer scientist. I'm not a biologist. But apparently this very general sort of AI has figured out has much accurate predictions than anything else we have out there, which surprised me. I didn't think that was possible, but there it is. But again, they still can't really do. We still don't have self-driving cars, for example. And that turns out to be think about it. Driving a car turns out to be a super hard problem that even Elon Musk, with all his Bitcoin, cannot solve. Not yet. So think about it. Is the quiz timed? Are the low-level ideas presented here ever used in practical situations? Are they limited more? So that's a good question. You don't typically run into this in practice every day. For example, undecidable problems. You don't come into it every day. But next, I'm going to try to convince you that there's something called intractability that has to do with space and time. And I'll get to it, I promise. If you can calculate the reaction, doesn't that mean randomness cannot exist? Again, this is something nobody knows. So far, we're treating machines as completely deterministic. And it's interesting. There's actually a problem in computational complexity. Look it up. It's called whether P equals BPP. Whether adding randomness actually buys you extra computational power. Again, there's no proof or disproof of it, but it turns out to be no, apparently not. So look it up. That's interesting. How does sorry, go ahead, Gene.
I'll throw in that once I got the idea of a universal Turing machine, that definitely had an impact on me, because once I understood that any general computer can compute anything computable, sometimes people get caught up in the hype of, whoa, now we have object-oriented languages, and this will give us a whole new possibility of computing that we never had before. If you know what Turing did with his proof, no, it's still a universal Turing machine. People say, oh, now the program's distributed over the network. Now it's got a whole new possibility. No, it's still a universal Turing machine. So it helps you cut through a lot of this hype. All universal Turing machines can compute the same problems. They may be able to do it faster, but that's that. So
exactly.
Getting that idea has been very helpful to me.
Exactly. So for example, Python and Java, you can write they may look different. Maybe something that's very short in Python, maybe much more verbose in Java, but it can do exactly the same. You can write the same programs, do the same things in both languages. The usefulness of programming languages might be in how it lets you express some ideas. So it might be more natural to compute something in some languages compared to others. But really, they're all the same. So let me go back to some more interesting, shall we say, more practical problems, more down-to-earth problems. The kind of problems you're much more likely to run into every day, right? Because someone asked you, and I forgot to share my screen. Sorry about that. Okay. And if you want to ask a question, feel free to interrupt me by voice. Don't just chat, because I can't keep up with the chat all the time, especially when I'm sharing my screen. Who cares about all this undecidability stuff, man? Gödel, schmedel, I don't run into it. Even mathematicians every day don't run into these unprovable statements. Actually, that's not strictly true. Even in mathematics, here's something controversial that I would say it's not original to me, but a lot of mathematicians don't take Gödel very seriously, which is not good. Because if Gödel is right, think about it. There's a lot of mathematical problems to this day, for example, that still remain unproven. Why is that? Is it because we're just not clever enough? Or is it because it's fundamentally impossible? Because then that's a death blow to the typical way that we do mathematics. So there's something called Goldbach conjecture, for example. I think the statement is, if I don't butcher it, every even number equal to or greater than 4 can be expressed as the sum of 2 primes. Yeah, I think that's the Goldbach conjecture. So how do you prove it? Well, how do you disprove it? That's much easier to do, because all you need to do is to find a single counterexample. So here's a computer program that would then take that statement and just try to find the first even number that's not the sum of 2 primes. Then I've disproved Goldbach's conjecture. So if this computer program ever halts, then I know that the conjecture is not true, right? And if I can prove that it runs forever, then I know that the conjecture is true. But guess what? Because of the halting problem, I can never tell whether this computer program, possibly this computer program, will have a halt or not. So therefore, see, that's a very simple way to understand Gödel. Actually, the halting reason is exactly the reason why you cannot prove or disprove all mathematical statements. Kind of interesting, isn't it? Even if it's true, there's just no way. No amount of human intelligence might be able to get you that proof. That is, at least if we're subject to the same limitations of computers. We don't know. So that's an interesting way to look at it. But let's get down to something more down to earth. Forget undecidability, Gödel, schmudel, all this crap. I don't run into it into my daily life. At least not if I'm not trying to build an antivirus. Let's talk about intractability. So even if a problem is computable, there is, in principle, we know that there is an answer. There is a computer program for it. You can find the exact answer. And one of these problems is, for example, the traveling salesman problem, which is a very cute problem. Let me pull it up. Traveling salesman problem is very easy to state. You are a traveling salesman back in the 1950s, back when they used to be a thing. Probably, unfortunately, ran out of business during the pandemic, I imagine. But back in the 50s, you had this guy, pack up his suitcase, going around selling vacuum cleaners, for example, which were a big new thing back then, right? Think about what a big deal that must have been. Kind of like what iPhones are right now, I imagine. But anyway, this guy has to go around all the cities in the United States, and he has to do it in a certain budget. He has to visit all of the cities once, and he has to meet a certain budget. Let's say, I don't know, $1,000, let's say, back in 1950s dollars. Maybe doable. Can it be done? For some instances, generally, so it turns out that this problem is what they call an NP-hard problem. If someone gives you the answer, claims to have the right answer, it's very easy to check it. You can do it in what they call polynomial time. So basically very quickly. That's all we care about. It can be done in practical time, okay? We don't need to get into gobbledygook technical jargon. Basically, okay. But to find the answer, guess what? All the intelligent people have been thrown at a problem. So computer scientists, back in the 70s, people like Cook and Levin and so on said, it looks like there's some problem that are called NP-hard problems that are very simple to state, like the traveling salesman problem. But we don't know how to do any better other than to just brute force the damn thing. That is to say, check every single possible solution of this combinatorial thing, right? You just try every possible way to attack the problem and see which one works. And that could be exponential. It has to grow technically super polynomially, but again, gobbledygook. Exponential is much easier to understand. So in case you are not familiar with exponentials, very, very easy to understand. By this parable, this lovely parable of the Persian vizier, basically a wise guy. Um, he helped the Persian king solve a very, I suppose, a computationally intractable problem. He helped the king with a very serious problem, and the king was so grateful and said, "Oh my God, what would I have ever done without you, man? You're the man. What do you want for it?" And this wise guy, being a wise guy, he said, "Oh, very simple. I just want all the grains of rice as follows: the following number of grains. Take a chessboard, which supposedly Persians came up with first. Well, at least they were one of the earliest players. How many grains of rice do you have in the first? There's 64 pieces. There's 64 boxes, right, on a chessboard, 8 times 8. So in the first box, you have 1 grain of rice. Now in the second one, you double that. So now you have 2. And you double that in the third one. Now you have 4. Then you double that and so on. Now you have 8. And then you have 16 and 32. You'll probably see where I'm getting at. This is how, 2 to the power of n, right? What's 2 to the power of 64? I forget what the exact number is again. Every time I look at it, I keep messing it up. Something like 10 to the power of 30. Basically, the king would have gone easily bankrupt. So exponentially growing problems grow very, very quickly. 64 is not a large number, but 2 to the power of 64 sure is. And if you keep doubling it, it only gets worse. Okay, 2 to the power of 65 is not just linear, it's double that. It's a lot bigger. So those are examples of problems that grow so quickly, and they don't seem to have a hidden structure. There's nothing that you can do to make, because it's random, because there seems to be no structure to it, there's no intelligence you can apply to these problems. So think about it. You've used Google Maps, right? Google Maps has to answer your question very, very quickly. If it doesn't, you get bored and you go somewhere else. But these problems, in general, these optimization problems, are very hard to solve accurately. You can get good enough answers. There's something called approximation algorithms. This is what people end up using in real life. They don't find you exact answers. That's why sometimes Google Maps, I live in New York. I used to live in New York. And, you live there and you say, hey, plot me the directions to get here. And you look at the answer, it comes back very fast. And you're like, well, that's stupid. I don't have to do this transfer at all. What are you talking about? But because of the constraints, the hidden constraints, namely one of them being that it wants to optimize your travel time in total, not considering things like number of transfers. But it cannot possibly optimize for everything. So it's a multi-dimensional problem, much harder than done. So it has to guess. Basically, it's an educated guess. And sometimes those guesses are not good enough. So that's something that you see in practice. Especially if you work in things like big data kind of problems, data science problems. I bet you will run into a lot of it. There's so many papers. So that's basically the P equals NP problem, if you've seen it. The English version of it is basically, can we search for answers to a class of problems as quickly as can verify the answers? Okay, here's another example of the problem. You guys know what factorization is, right? Basically, it's breaking down a number to the multiplication of its primes. Am I getting this right, Gene? Every number can be, yes. Every number can be expressed as the multiplication of primes. That's the fundamental theorem of arithmetic, I think. And so
unique factorization. There's a unique factorization of every integer into primes.
Yes. And so if Scott Aronson puts it, thank you. And Scott Aronson puts it very, very brilliantly. Here's how to understand NP-hard problems. Very easy to explain. I give my grad student a very large number and I tell him to go factor it. I don't know how long he will take, but I can always check whether he's BSing me or not. Because when he comes back with a factorization, I can easily multiply those numbers together to check whether he was right or not. So you see, multiplication is a lot easier problem than factoring the number in the first place. So it's a one-way function in this sense. It's easy to go in one direction, but not the other way. And that turns out to be extremely useful because you can, if you assume the hardness of a problem, you can come up with basically cryptography. What is cryptography? Think of it. One way to think of cryptography is you have a plain text that you want to make it a secret. So you get something called a ciphertext out of it that looks like random gobbledygook to your enemies who's intercepting your communications in the middle. But because you have the secret key, you can easily recover it. But for anyone without a key, they basically have to brute force the space of all possible keys, which can be exponential. All I have to do to make the problem harder is to just double my key size. I don't even have to double my key size. I just add one more, and suddenly it's 2 times harder. Sorry, go ahead.
So this would be good for me hiding my preparations for the boxing match from Professor Arfawi, so he couldn't tell what strategies I was going to use.
Not only that, but I wanted to say, all the cool kids these days are here. Besides Gamestonks, they're also buying Bitcoin. Your Bitcoin basically depends on computational complexity, on interactability, on the assumed hardness of these problems. There's no proof for it. Nobody knows. This is at least $1 million open problem. The Clay Institute will give you $1 million, which I think is severely underrated. Because if you can crack this problem, if you can find answers as quickly as you can verify them, we're dead. You can actually trivially mechanize mathematics, actually. Because then you can quickly just brute force through proofs and then find proofs easily. At least for small, interesting statements that we care about. So it's interesting, but it seems as if nature abhors shortcuts. You know how do usually, I like to joke that they lie to you and say nature loves shortcuts. Yeah, in some cases, but generally she actually doesn't. It keeps life interesting. It means you have to, sort of like the way evolution works, you have to do trial and error and see which one works. Is this better? I don't know. Oh, turns out that was a terrible mutation. Try this. The coronavirus is sort of arguably doing this, right? It's mutating so many times. And the ones that survive are the ones that much more infectious. So believe it or not, your cryptography, if you're using the Signal app or WhatsApp or Telegram, they all depend on this very, very useful practical property of computer programs. And it doesn't seem to be a mathematical fact. It seems to be a physical fact. It's a deep physical fact of the universe. Because like I said, no one's able to prove anything about it. It doesn't seem to be a problem that's amenable to purely mathematical attack. Because you have to explain why it's not physically possible. Why it's not possible to say compute faster than the speed of light. That's not a mathematical thing. That's a physical thing. At least that's what people like Scott Aronson say. He's a computational complexity scientist who studies these problems, especially using quantum computers. Yeah, so your Bitcoin. So there, useful stuff. Hopefully someone found that useful. Hopefully you can sleep at night knowing that your precious, precious Dogecoins are protected by an assumption. Nobody's proved this stuff. It's just assumed that the problem is hard. Okay, so I think I'll stop there. I can go into Wolfram stuff and everything, but I think I've said a lot, and I think some people might be confused. And the point is not to confuse you, it's just to try to give you a taste for, give you such a broad sampling of what computation is about that hopefully you get more interested to explore this stuff deeper on your own. Thanks.
Thank you.
Gene.
That was a wonderful talk, and it precisely. We're going to have a series of talks like this, and we shouldn't imagine that we're going to come out of any of them that, oh, now I've completely mastered cybersecurity. Now I'm the world's expert on this. These are intended to get you interested and let you know that there's a lot out there to learn about, right? And I think Trishank did a wonderful job whetting our appetites for learning more about computation. So lovely. So why don't people ask questions? Again, it's okay. Well, very good, Ari. You're quicker than most of us. If someone has completely mastered the field from this talk, the quiz will be out. Where we need to edit it a bit. I'm actually going to try when I listen to the lecture to throw in a couple questions myself, perhaps. Professor Arfawi may do the same. We had One of our TAs, Amadou Diallo, is here. Paloma St. Clair, another TA, was here. There's so many people. I'm not sure if she's still here at the moment. But so our TAs listening in may also come up with questions. So you may type in chat, or you may speak and ask questions. So is there any questions for our guest?
Should you buy Bitcoin? I still don't know the question to that one. That one seems to be undecidable.
Well, sorry, I lost the beginning of that. What was that?
Oh, sorry. I made a terrible joke, which is, should you buy Bitcoin? I'm afraid I can't advise you on that. Not only for legal reasons, but because it may be undecidable.
Right. Yes, Dominique, the quiz will be timed. We'll have a large window in which to do it, but once you start it, you'll have limited time to finish, as it's just multiple choice. So, it's not going to be crazy. You're not working on long problems. Is there really something called garlic coin?
The students are hilarious.
So Remington asks, can we do it from a mobile device? It's gonna be up on Gradescope. I haven't tried Gradescope from a mobile device. So I will, though. Let me have a look and see.
I think you could. I think you could.
Yeah. The issue would be, so theoretically, for instance, you can use Albert from a mobile device, but as a practical matter, oh no, you don't want to. It looks just it's horrific. It looks so bad that it's just about impossible to use. So I know theoretically, because Gradescope runs in a browser, theoretically we can do it from a mobile device. It's not like the halting problem, which is theoretically unsolvable.
No, this is great. This is beautiful.
It may be like
great. Sorry, go ahead. It's a great demonstration of universality. So in theory, yes, your phone can do exactly everything that your desktop can do, but in this case,
but don't do
it. Yeah.
Yeah, as a practical matter, it might be like solving the traveling salesman problem. Practically, you may not want to run it. So we'll take a look and see how it looks on a mobile phone. But
your phone is a computer.
Yeah, it is. So Remington, if it turns out that it's impossible from a mobile device, we'll figure out something for you, okay? So Dominique's used it on the phone, and she says it's not bad. So we're going to give you enough time that as long as it looks reasonably good, you won't have a problem. Okay. So Swanya, you threw out to the whole house, what is a workday like for you? There's 180 of us here. Should everyone answer?
Oh no, I've been singled out.
Oh, okay. There we go. That's
well, this is bad because I'm answering
for you.
Sorry, go ahead. Oh, so I have to answer this publicly. So now
what do you do at work?
Yeah, exactly. Now my boss has to know what my
you don't have to. You don't have to tell us how much time you take off during the day. Just when you are working, what do you do?
So besides Facebooking all day, no, I'm joking. But and getting into little Twitter fights with Gene every now and then, which is entertaining. But so I work in cybersecurity, as Gene mentioned. And it's a very interesting job. Not only does it pay the bills, but it's actually, we live in interesting times. So recently, and my specialty happens to be securing software updates, which is what my R&D at work at NYU was when I was working along with Gene. Um, Basically, the problem is, think about it. So you might use Python and Java and whatnot. You're getting a software package from somewhere. Imagine if they get hacked. And recently, this sort of happened, right, with something called the SolarWinds attack. I'm not sure how many of you heard of it. It's kind of a big deal in the sense that the U.S. agencies got hacked, like financial institutions got hacked. They basically compromised. So think about it. These days, when you install apps in your phone, who's building that app? It's a robot. As I like to joke, it's robots, but it is true. It's robots sitting in the cloud, building, packaging that app, taking your source code, building it into an app, and sending it to millions of users. Now imagine what happens. No, they don't even have to steal the source code. They actually didn't do that. Although they used it to steal Microsoft source code later. But what they did was get into basically SolarWinds. It's an enterprise monitoring company. They got into SolarWinds robot and took over the robot. Now the robot is a bad guy. I like to joke that automation is a powerful thing, but it's like an assault rifle, very powerful but very dangerous. Now someone's got your packaging robot and it's making it build bad stuff that you didn't release. So that's the sort of attacks that I worry about. My colleagues and I worry about, and we figure out how to actually practically solve them. And the tool, yeah, basically that's my job. I figure out how to build security systems that assume that they will be hacked. So that's a good way to think about cybersecurity. Don't just worry about all the ways that you will be hacked. You cannot possibly close all the gaps. Just assume you will be hacked and then design your system in such a way that even if you get hacked, you don't lose the keys to your kingdom. And I work on two particular open source technologies called the Update Framework and in Toto. And I'm happy to send you links. Yeah, so basically my work days, sorry? Oh. So basically, my work does is some days I'm busy designing how to secure systems, and some other days I'm busy coding, implementing the solution. So it's a very interesting, very highly varying job. So hopefully that roughly gives you the idea.
Hey, I have a question. This is to everyone. So an MTA turnstile, can it be modeled as a finite state machine or a Turing machine? What do you think is best?
But we didn't explain what, at least I don't think I remembered explaining finite state machines.
Well, you talked about it briefly.
Explain, Salim?
You talked about it briefly, yes.
Yeah, basically finite state machines, you can think of it as basically equivalent to something called regular expressions, if you've ever seen it. It's just little machines that literally have very bounded memory and they can move from one state to another given an input. So for example, you can compute the parity of a number, whether it's even or odd, using two states. Right? You just flip between the two states. But anyway, maybe something to think about, and maybe that could be a quiz question. Actually, make it a quiz question.
Yeah, because a finite state machine is a machine that has like something called a state, and it can receive inputs, and the inputs can change the state. So I would say, yeah, we'll leave it as a quiz question. I'm not giving you the answer now.
Yeah, maybe students should look up what finite state machines can and cannot do and try to model them. And look at Turing machines too while they're at it. They're actually not easy to program. They're actually rather horrible to program in. You think assembly programming is bad? Try programming a Turing machine.
I actually know someone whose first programming was toggling switches to enter all the zeros and ones that were needed into memory and then hitting a run button, which that had to be interesting programming. All right, well, I'd like to thank our guests. This was a wonderful talk, a great start to the semester. We will be announcing the quiz later today. All right. And you'll have plenty of time to do it. So relax. Frankie says relax. You know, don't worry about it. You'll get an announcement. You'll have lots of time.
And rewatch
Okay,
this
so,
amazing lecture.
Yeah. All right. Thank you all. We'll be in touch through NYU classes later today. And we'll see you all next Friday live again. So thanks, everybody.
Thank you.